Well, hi guys. I sure do miss having you around. Here I'm going to attempt to make a video on my iPad about what's going on in our calculus class. We're on section 4.3. We're going to talk about what the first derivative tells us about the graph of a function. So here I've drawn you a continuous function. And on this graph there are peaks and valleys and a sharp corner. Remember that those were the critical numbers of the function. At the critical numbers, the tangent line is either going to have zero slope, like here and here, and at a sharp corner we have a critical number, but we can't draw a tangent line there. There will be the tangent line. The tangent line does not exist right there. If I drew some more tangent lines around those critical numbers, where the graph is falling like this, the tangent lines are going to have negative slope. Negative slope is going to tell us that the graph is decreasing. On these two intervals, the tangent lines can be drawn like this, so they have positive slope. Positive slope is going to tell us that the function is increasing on that interval. So let's write that down. Intervals on which f prime is positive are going to indicate that the function itself is increasing over that interval. And when the derivative is negative on some interval, then we know that the function decreases. Don't want that. Boom. Looky there. On the eraser, get back on the point. So the sign of the derivative is going to tell us whether the graph is going to be rising or falling. If the sign of the derivative changes from negative to positive around a critical number, then we're going to know that that critical number is down here at the bottom. The sign changes from negative to positive, negative to positive. In which case, each of those critical numbers are going to be called relative minimums. The critical number here, where the derivative changes from positive to negative, is the location of a relative maximum. That is called the first derivative test for relative extrema. It just tells you what kind of extreme value our critical numbers are. So in each case, we're analyzing the function at the critical number. Let x is equal to c be a critical number for a function. We look at the sign of the derivative around the critical number. If the derivative is positive on the left of the critical number and then negative on the right, then that tells us that the direction of the function is that it climbs and then falls. If that happens, then we know that the critical number is the location of a relative maximum. F of c is a relative maximum, rising to the left, falling on the right. If it goes the other way, then I know that the direction of f is that it falls, hits a minimum, and then rises. So our conclusion is that f of c is a relative min. It's possible that the sign doesn't change around a critical number, in which case it's not a max or a min. Maybe the graph just kind of briefly flattens out, but it doesn't turn around, like you'd see in the graph of y is equal to x cubed around the origin. Let's look at a quick example. of what we'll be doing here. Let's take a function. Let's get just a polynomial. I don't know, nothing easier than a third degree polynomial, right? X cubed minus 6x squared. How about that one? We pretty much already know what it looks like. A third degree polynomial is probably going to rise, fall, and then rise. But let's go ahead and do all the stuff with the derivative. And let's find each of the following. Let's find the critical numbers. Let's find the intervals on which it's increasing, on which it's decreasing. And then from that, decide where we have a relative max, if any, and where we have a relative min. And then we'll put it all together and sketch a graph. All of the information above is found by looking at the first derivative. So let's knock out the first derivative. F prime is 3x squared minus 12x. Let's set the derivative equal to 0. See where we can find the horizontal tangent lines. I'm going to factor. I can pull out a 3x, and that leaves an x minus 4. That gives us two critical numbers. This factor is 0 when x is 0, and this factor is 0 when x is 4. So those are our critical numbers. To answer the rest of it, we make our number line. Put 0 and 4 on here. And let's determine the sign of the derivative. And I'll go back and I'm going to plug the test numbers back into the factored version of the derivative so that I don't have to really crunch numbers. For instance, let's take a -1 from here. This factor is going to be a -3, a -5. Negative times negative is positive. If I try a +1, this factor is positive, but this factor is negative. Positive times negative is negative. And now we'll try a +5, and I'll get 15 times 1. Well, that's positive. So that tells me the direction of f. It rises where the derivative is positive, falls where the derivative is negative. So let's go over here and write that as intervals. It increases where the arrows are going up, so that's to the left of 0, as an interval that's from -infinity to 0. And then beyond the 4, so union 4 to infinity. It decreases in between 0 and 4. And now let's look at the direction that the graph is moving, follow the arrows, and make a decision on what kind of extreme value we have everywhere. If the graph is going from rising to falling, then that means this critical number at x is 0 is a relative max. The y value is the maximum value. The other critical number gives us a min because the graph drops to the left and then rises to the right. So we have f of 4 is the relative min. If we want to get the graph, we'll have to go back and plot those numbers in here. When x is 0, y is 0. When x is 4, I've got 4 cubed minus 6 times 4 squared. 4 cubed is 64. 4 squared is 16. 6 times 16 is somewhere in the neighborhood of 96. So I've got a negative something something. How about a negative 28? The number's not important. Just give me some idea on my graph. So let's plot those 2 points, 0, 0, and 4, -28. Boom, nailed the 0, 0. And let's just make our scale big enough to see. Let's say that this is the ordered pair 4, -28. Now I know the graph is going to have to rise until it hits this point. Then it's going to fall between 0 and 4, and then rise again. Then I know that this thing here is a polynomial, so it should do all that motion between the points in a smooth manner. So let's just now draw a smooth curve. Rise, fall, rise. And there you have it. The first derivative almost always can tell us what the graph looks like. Almost always. We might need the second derivative to help us out a little bit to tell us how the graph bends. For instance, if we just look at the graph of y is equal to x cubed, its derivative is 3x squared. The derivative is 0 only when x is 0. But if I look at the sign of the derivative, I get, since it's squared, the sign of the derivative is always positive, which means my function increases on both sides of the critical number. I know my graph is not a straight line. At 0, y is 0. The graph has to increase here and continue to increase. And there's a couple of ways it can do that. It can do it like this, and then like that. Or another choice would be that it could go like this, and then like that. But we know what the graph of this looks like. It's the first one. We know that it bends downward in here and then upward over here. That's something called the concavity of the graph. And I'm going to show you that we are going to use the second derivative to tell us the concavity of the graph.